Today we are going to look into one of the most important pieces of industrial equipment in the world, the blast furnace. We will be exploring how tiny unwanted impurities can cause major problems, acting as a hidden saboteurs that increase fuel consumption and drive up cost. Specifically, we will take a quantitative look at the impact of three harmful elements, potassium, sodium and zinc, and let's get started. So, who are these culprits? We are talking about impurities elements like potassium, sodium, and zinc. And these elements are commonly found in raw materials fed into furnace like iron ore and coke. They are called harmful because they cause serious operational problems. Studies have shown that they can lead to the formation of scaffolds on the furnace wall, cause severe damages to the refractory brick that line the furnace, and even make the coke degrade and break down. Ultimately, all these issues led to an increase in coke ratio, which means you have to burn more expensive coke to produce same amount of hot metal. The challenge of the furnace operator is that there is no single uniform standard for controlling the loads of these elements, which make managing them very difficult. So, how do these elements cause so much damage? The key is that they get trapped in a viscous cycle of circulation and accumulation inside the furnace. Here is how it works. First, in a very hot lower region of the furnace, the oxides of potassium, sodium, and zinc are reduced into vapors. For example, zinc oxide react with carbon monoxide to form zinc vapor and carbon dioxide. This is an endothermic process, meaning it absorbs a lot of heat. Second, these hot metal vapors travel upward with the furnace gases. And third, when they reach cooler upper part of furnace, the vapors are reoxidized and deposited back onto the raw material that are moving downward. This leads to the final step as those materials descend back into the hot zone. The elements are reduced all over again, restarting the entire cycle. This continuous loop leads to a massive buildup or accumulation of these harmful elements inside the furnace. This circulation and accumulation directly harm the furnace efficiency in two major ways. First, it causes decrease in gas utilization. The chemical reaction involved in this cycle consume carbon monoxide and produce carbon dioxide inefficiently. This means the gas is not being used as effectively as it should be for the main job of making iron. Second, it leads to an increase in heat consumption. As we just saw, the reduction of these harmful element oxide is an endothermic process, meaning it consumes a significant amount of heat from the furnace. The bottom line is simple. With less efficient gas use and higher heat demand, the furnace is forced to burn more coke just to keep up. So, how much damage are we talking about? Researchers in this study uses a tool called a Rist operation diagram to quantitatively measure the impact. The Rist diagram is a method used to analyze energy and oxygen transfer within the furnace. The study found that the presence of harmful element changes key point on the diagram, which causes the slope of the operating line to become steeper. A steeper slope directly corresponds to a higher coke ratio. Based on data from commercial a 70-80 cubic meter blast furnace, the study calculated the specific increase in coke needed for each ton of hot metal produced. The coke ratio increased by 14.2 kg due to potassium, 35.8 kg due to sodium, and 9.3 kg due to zinc. These are the significant amount that directly impact production cost. A key finding from the research is that not all harmful elements behave the same way, and the damage they cause depends on how you measure the impact. So let's first look at accumulation times, which is a measure of how much an element build up inside the furnace. Based on this, the order of influence on the coke ratio is sodium, then potassium, and then zinc. This means sodium is the most damaging when it allowed to accumulate, which highlight just how important it is to use right slag chemistry to remove these alkali metal. But if you look at the load, the amount of each element entering the furnace with the raw material, the story changes based on the load. On the order to influence is zinc, then sodium, then potassium. This tells us even a small amount of zinc in the raw material can have a disproportionately large negative effect on fuel consumption. The study went on step further and asked why coke ratio increased. It's mainly due to poor gas utilization or extra heat requirement. The results were clear. The primary driver is the increase in heat consumption. The extra heat consumed by the harmful elements reaction account for 55.9% of the coke increase from potassium, 60.9% from the sodium, and 60.9 from the zinc. This means that over half of the extra fuel is burned just to supply the energy that being hijacked by this viscous cycle. So let's wrap up with the key takeaways from this research. First, harmful elements are costly. The circulation of potassium, sodium, and zinc significantly increase coke consumption, primarily by increasing the furnace heat demand. Second, different elements have different impact. The impact of each varies depending on whether you are looking at its accumulation inside the furnace or its load in the raw material. And finally, this all points to one crucial conclusion. To run a blast furnace efficiently, it is vital to restrict the load of potassium, sodium, and zinc in the raw material you feed into it. By quantitatively understanding how these elements behave, operator can make more informed decision to improve efficiency, reduce cost, and create a more stable production environment.